Okay, so in this video, we are looking at the beginning of our surds and indices topic, and we're going to start by talking about irrational numbers, of which surds are an example. So a surd is an irrational number. So before we get to that, let's talk about what are irrational numbers. And before we can get to that, let's talk more generally about the number system. So this diagram here sort of illustrates how our various different types of numbers sort of relate to one another. So when we first start learning about numbers, when we're a very young child, we learn about the natural numbers. And the natural numbers are just what we might loosely refer to as the counting numbers. 1, 2, 3, 4, 5, 6. So positive whole numbers, okay? So natural numbers 1, 2, 3, 4, 5, etc. Okay? Then down the track, quite a lot further down the track really, sort of late primary, early secondary school. Although a bit before that we might add in 0, but we talk about the integers. So the integers include all of the natural numbers, so every natural number is an integer. But in addition to those, we add in 0, okay, and then we head into negative territory. So -1, -2, -3, -4, etc. So still whole numbers, but integers incorporates positive and negative whole numbers as well as 0. Okay, so integers includes all the natural numbers, so that's why in the diagram I've got the natural numbers drawn as part of the integers. Okay, then integers and natural numbers are actually part of a larger set of numbers that we call the rational numbers. And rational numbers are anything that we can write as a fraction. Okay, so that's not everything between all the whole numbers, but it is most things. Okay, so everything that we can write as a fraction, 1/2, 0.25. So even though we write it as a decimal, it can be written as a fraction. It's 1/4. Okay, it doesn't have to be less than 1. It could be 7/3. It could be 364/25. It could be 0.13597, which can be written as a fraction. Most efficiently, you could write it as a fraction by writing it as 13597/100,000. So anything that can be written as a fraction is a rational number. Okay, so then if we think about this idea of real numbers, so in terms of when we draw a number line, when we draw a number line, 0, 100, negative 20, whatever it might be, we can mark a point at any point on this number line, and it's a real number. This is the real number line. Now, yes, you might say, what are unreal numbers? Well, there actually are unreal numbers, imaginary numbers, which if you head down a specialist maths path down the track, you will learn about those. But for all intents and purposes in year 10, and even if we're heading down a maths methods pathway over the next 2 years, our whole entire world of numbers is the real numbers. Okay, so everything is a real number. Well, again, let's forget the imaginary world, which is outside of our world of thinking. Everything is anything on the number line is a real number, and those real numbers are either rational, that is, they can be written as fractions, or irrational. Okay, that is, they can't be written as fractions. So irrational numbers are where surd sits. We're also familiar with one other really common irrational number, and that is the number pi. Okay. Now pi, we know, is approximately equal to 3.14. Now someone might have told you that pi is the same as 22/7. No, it's approximately 22/7, but it's not exactly 22/7. Okay, so the only exact way to write pi is to call it pi. As a decimal, it has to be rounded off. As a fraction, we can approximate it with a fraction, but it is not exactly equal to that value. So irrational numbers can't be expressed as fractions. Okay, and their decimal representations would go on and on forever without repeat. Surds are also examples of irrational numbers. The simplest surd is √2. √2 is approximately 1.4, I think it's 1.42 or 1.41. Square root of 2. Oops, sorry, square root of 2. I'm just over here on the CAS, which is playing a bit. There we go. So yeah, 1.41 to 2 decimal places. But as you see, that goes on and on forever without any kind of repeat. Okay, obviously that's not going forever, but that's as far as your CAS will show you. But it doesn't repeat, it doesn't recur, it doesn't terminate. It is So if we're going to write root 2 as a decimal, we have to round it off at some point, and therefore its decimal representation is not exactly the same as it. Okay, so that's why I've written this approximately equal to as opposed to equal to. So the only exact way to write an irrational number is to write it as pi, or to write it as root 2 or root 5 or root 7. Just to make a point, root 4 is not an irrational number because root 4 isn't a surd. It can be simplified to 2, which is a natural number, so hence a rational number. Okay, so irrational numbers can't be expressed as fractions. Their decimal representations go on and on forever without repeat. Okay, so all real numbers can be classified as either rational or irrational. Rational numbers, as I've said, can be expressed as a fraction, and their decimal representations either terminate, so for example 0.5, 0.25, 0.4, 0.376, okay, or they repeat, 0.3 recurring, 0.12 recurring, okay, whatever it might be. So examples of rational numbers, they can be positive, negative, decimal, fraction, whole number, etc. But they have to be able to be represented as a fraction. Their decimal representation has to terminate or repeat. Irrational numbers are all the things that are not rational numbers, okay, all the real numbers that are not rational numbers. So they cannot be expressed as fractions, and their decimal representations neither terminate nor repeat. Okay, so as I said, examples of irrational numbers include pi and surds such as root 2. Okay, then let's talk about radicals versus surds. Any number that we write with this square root sign, okay, is actually called a radical sign. Any number we write using the radical sign is a radical. So for example, root 3, 2 root 5, which is just 2 lots of root 5, square root of 1 on 6, square root of 16, cube root of 27, they are all radicals. However, they are not all surds. Only the irrational radicals are called surds. So for example, root 16, that's not a surd because that simplifies to 4 and it's not irrational. Okay, cube root of 27, that's not irrational because that simplifies to 3. Okay, but these ones all would be irrational numbers and hence they would be surds. They cannot be simplified to a point where they don't include the radical sign. Okay, so essentially, if in its simplest form your radical still involves the radical sign, it's a surd. If, however, your radical can be simplified so it doesn't involve the radical sign, it's not a surd. Okay, so determine whether each of the following numbers is rational, radical, or a surd. That is an irrational radical. If it is a surd, find its value correct to 4 decimal places. So it's either a rational radical or an irrational radical. They've all got radical signs. Okay, so root 5 can't be simplified any further than that. We'll talk about simplifying surds in the next video, okay? And so this is a surd. That is an irrational radical. And to 4 decimal places, let's have a think about before we do it. Oh, sorry, roughly how big we're expecting root 5 to be. Well, we know root 4 is 2, and we know that root 9 is 3, and so therefore root 5 is going to have to be somewhere between 2 and 3. And given that root 5 is closer to root 4 than it is to root 9, it's probably going to be closer to 2 than it is to 3. So let's press Control Enter to get an approximation for this surd. So as I said, it goes on and on forever without repeat. We cannot write it exactly as a decimal, but the question asks me to find its value correct to 4 decimal places. So we're rounding it off to 4 decimal places. And in this instance, that would be 2.2361 to 4 decimal places. Okay, root 36 is not a surd because it equals 6. Okay, so that is a rational radical. Root 72, it can be simplified. We'll talk more about simplifying down the track, but it's not the square root of something squared doesn't equal 72, and so therefore it's going to have to be an irrational radical or a surd. And so we can approximate its decimal. Let's think about square numbers that are near 72. 81, that's 9 squared, okay? And 8 squared is 64. So 72 is somewhere between 64 and 81. It's roughly in the middle of those two. So we would expect root 72 to be somewhere around 8.5. Let's have a look. Square root of 72. It's important that you can sort of roughly approximate the size of the surds in your head. And it's just about thinking about square numbers that are near this particular value. So as I said, roughly around 8.5, which is about right. 8 point, now we want 4 decimal places, 4, 8, 5, and again we round up to 3. Root 81, Okay, well that's not a surd because that's equal to 9, and so that is a rational number, a rational radical. Root 25 on 49. Okay, well, we'll talk more about properties of surds down the track, but we can break this up as root 25 over root 49. Okay, when it's division and multiplication, we can do that. We'll talk about the properties in a minute. And so root 25 on root 49, root 25 is 5, and root 49 is 7. Okay. Again, you don't really need to be able to think about that. You just need to be able to think about the fact that 5 on 7, sorry, they're not equal, but 5 on 7 squared is 25 on 49, and so therefore the square root of it is going to be 5 on 7. Okay, so we can simplify it so it doesn't have the radical symbol anymore. It's a fraction, but fractions are rational numbers. It's a rational number. Root 1/10, okay, well root 1 is 1, but root 10 is going to still be a surd, and so this is going to be a surd, an irrational radical, and let's approximate that as a decimal, square root of 1/10. Now a bit harder to perhaps approximate in your head. I can think of 1/9 would be the square root of 1/9 would be a third, and 1/10 is a bit smaller than that, so it's going to be a bit smaller than a third, so a bit smaller than 0.3 recurring. That is 0.3162. 1 on 64. Okay, well, square root of 1 on 64 is going to be square root of 1 on the square root of 64, so it's going to be 1/8, and so that is rational. It's not a surd. And the square root of 3 on 14, neither 3 or 14 can be square rooted to produce a whole number, and so this is going to be a surd. Let's get an approximation for that. Square root of 3/14 is approximately 0.4629 to 4 decimal places. Okay, so just giving you a bit of a sense of being able to think a bit about the size of a surd, okay, without actually potentially having a calculator. So unless you're asked to give the answer rounded to a particular level of accuracy, you would just leave it as a surd. That's the most exact way of writing it, but this question specified that we give our value correct to 4 decimal places. Okay, let's just have a quick look at some simple properties of radicals. So if we would have the square root of a and then square it, if you think about that, if you've got a number, whatever it is, 2, and you take the square root of it and then you square it, well, square rooting and squaring, they're just opposite operations, so that's just going to take us back to 2. Let's think about that for a number where we can actually calculate the square root. So if we had the square root of 4 squared, well, square root of 4 is 2, and then we square that, well, it's 4. And that would be the same, square root of 9 squared, or square root of 9 is 3, and we square that, we get back to 9. So if you square root and then square a number, you just get back to where you started. So the square root of a squared again is just going to be a. We could also think about this as the same as the square root of a times the square root of a, okay? And regardless, it's just going to give us a. Again, square root of a squared, it's just the same thing but in reverse. So if you take 4 and you square it and then you square root it, it's going to be square root of 16, which is 4. Okay, so of course you're going to get back to 4 if you square and then square root, because those two operations are opposite to each other, and we get back to a. Now, if we have the square root of a product, so square root of two things being multiplied together, we can break up the square root. Square root of a times b is the same as the square root of a times the square root of b. Okay. Similarly, if we have division, square root of a divided by b is the square root of a divided by the square root of b. However, if we have addition or subtraction, we cannot break up the surd in this way. Let's look at an example. If I have the square root of 9 plus 16, okay, that is not the same as the square root of 9 plus the square root of 16. Okay, square root of 9 plus 16 would be root 25, which would be 5. Square root of 9 is 3 plus the square root of 16 is 4. That would be 7. 7 doesn't equal 5. Okay, you cannot break up the surd if there's addition. Similarly, if it was subtraction, you also cannot break up the surd in that way. However, multiplication and division, we can split up the surd as two separate surds. Okay, let's simplify each of the following. So square root of 2 squared, again we're taking 2, we're square rooting it and then we're squaring it, so we're just going to get back to 2. Okay, square root of 2 cubed. Now let's think about when we cube something, it's the same as squaring it and then multiplying it by itself again. Okay, so this is just root 2 times root 2 times root 2, but that is root 2 squared. So it's root 2 squared and then times root 2 again. Now we've already looked at root 2 squared over here. Root 2 squared was 2 times root 2. Now if we write 2 times root 2, in the same way that with algebra, if we're meaning 2 times x, we can write that as 2x. The same is true with surds. 2 times root 2, we can write that as 2 root 2. 3 root 5 squared. Okay, so indices, I know we're going to revise those a little later on in this topic, but these basics we should be aware of. So we know that if, for example, we have 2x all squared, it's 2 squared times x squared, so 4x squared. So we can apply that squared. When we have multiplication, 2 times x squared, we can just square that thing and square that thing. Okay, so this is 3 times root 5 all squared. So this is 3 squared times root 5 squared. I wouldn't write out this step, I'd just do it, but just to be clear about what's happening. So 3 squared is 9, root 5 squared. If you've taken 5 and you've square rooted it and then you've squared it, it's just 5. 9 times 5 is 45. Okay, D, we have a fraction, all squared. Again, we know if we have a fraction, if we have A over B all squared, we can square A and we can square B. Okay, and that's because A over B all squared, means A over B times A over B, which means A times A squared on the top, over B times B squared on the bottom. Okay, so we can go straight here. So in this case, we can just square the numerator and the denominator of this fraction. So this is going to be 2 squared over root 7 squared. Now 2 squared is 4 over root 7 squared is 7. Okay, E, 2 root 7 times 3 root 2. Okay, a couple of things to look at here. So first of all, 2 root 7 means 2 times root 7. And then we're multiplying that by 3 root 2. Remember, 3 root 2 just means 3 times root 2. So all we have here is multiplication. 4 different things being multiplied together. Now we know we can multiply in any order and still get the same result. And so I'm going to do 2 times 3 to make that 6. And then I'm going to think separately about the root 7 times root 2. Okay, so I wouldn't write out these 2 steps. I would just do it. 2 times 3 is 6. And then if we go back up here, our properties of surds, we looked at how we can split up a surd. So if we have the square root of A times B, it is the square root of A times the square root of B, but that works in reverse. If I have the square root of something times the square root of something else, I can put them together as one surd. Okay, so this, where I have the square root of 7 times the square root of 2, that is just the square root of 7 times 2, which is 14. Now, down the track, we will need to make sure that that surd is in simplest form, but for now, the examples I'm giving you, they are in simplest form at this point. We'll have a look at simplifying in the next video. Okay, part F, root 3 times negative 4 root 3. Now, this bracket's not really doing anything. Technically, it would still be exactly the same calculation without it. It's just emphasising that the negative belongs to the 4 root 3. You're not subtracting 4 root 3, but the multiplication here means that you're not subtracting anyway. So it's not necessary, those brackets. They're just there to help clarify what's happening. So essentially what we have here is we've got root 3 times negative 4 root 3, which is negative 4 times root 3. Now remember, we've just got 3 things multiplying together there, and so we can multiply in any order. So let's instead think about negative 4 times root 3 times root 3. Remember, root 3 times root 3 is root 3 squared. Again, I wouldn't write out that step. I understand that and I'd do it straight away in my head. Root 3 all squared. You've got 3, you're square rooting it, and then you're squaring it, so it's just going to be 3. So it's negative 4 times 3, which is going to be negative 12. Okay, G. Now again, let's go back up here and look at this property of the surds here. We looked at the fact that if we have the square root of a fraction, a divided by b, we can split it up as the square root of a divided by the square root of b. But similarly, we can then go backwards as well. If we've got one surd divided by another, if it's useful to us, we can then write that as one single surd of that fraction. One single square root of that fraction. So here where we've got root 75 over root 3, we could just write this as square root of 75 over 3. And 3 goes into 75, that's the square root of 25. And actually the square root of 25 is not a surd at all, it's just 5. Similarly here in part H, same kind of idea. So root 32, remember that's just one lot of root 32. So let's just sort of think about that fraction and that fraction separately. If we think about this as just being 1/2 times root 32 over root 2. 1/2 times, now root 32 over root 2 is square root of 32 over 2. Now 32 over 2 is 16, so that's the square root of 16. And the square root of 16, again, that's not a surd, square root of 16 is 4, so 1/2 times 4, and then 1/2 times 4 is 2. And then finally, part I, we have the square root of 12 and 1/4. Now, let's be careful about mixed numbers. I really don't like mixed numbers. I really want you to move away from thinking in terms of mixed numbers and trying to work in terms of mixed numbers. So the minute I have a mixed number, the first thing I want to do is write it as an improper fraction. And the reason I need to be careful here is because 12 and 1/4 is 12 plus 1/4. So I cannot just do root 12 plus root 1/4. Okay? That's not how surds work. We can't break up surds like that when there's addition or subtraction. So I need to be able to think about 12 and 1/4. So 12, remember, this is 12 plus 1/4. 12 is 48 quarters plus 1/4. And so actually what we have here is the square root of 49 quarters, which is the square root of 49 over the square root of 4. And so we have 7 over 2. Okay, so the practice here is from a worksheet looking at irrational numbers and some basic properties of surds.